Okay, continuing our practice with finding concentrations. Reminder, the formula that we're using for all of these things is that your acid concentration, you can write H plus if you want, H3O is a little more true, times the hydroxide concentration equals the ion product for water, or the autoionization product for water, or the equilibrium constant of the autoionization of water. Anyway, 1 times 10 to the minus 14 is this number at room temperature. If water is hotter or colder than ambient, then this number changes, I'm sorry to say, but we're never going to do that to you in this course, so you can just stick with 1 times 10 to the minus 14 for now. Okay, let's see what we can do with this. They want both concentrations this time, so here we have a top 6 acid. Math is easy for those. Top 6 acids just convert 100% to H3O, so for this one, the H3O is automatically 0.5. Because 100% of the hydrochloric acid converts to H3O. Now we need the OH, and you'll get that by doing this formula. Divide both sides by H3O, and you get hydroxide is Kw divided by H3O, so 1 times 10 to the minus 14 divided by 0.5. Dividing by 0.5 is the same as multiplying by 2, so we're just going to get 2 times 10 to the minus 14 moles per liter of hydroxide. HNO3, this is nitric acid. It's another top 6, so again we could say the H3O is just the same as the acid. Every single HNO3 turns into a hydronium ion, and so again our hydroxide will be 1 times 10 to the minus 14 divided by 2.5. 1 divided by half is 0.4. Shift that up to 4, drop this down to minus 15, and we get 4 times 10 to the minus 15. And again, that's moles per liter. You know it's moles per liter. I'm not going to write that in every time. This is going to get crowded enough as it is. Okay, so these two solutions, very high H3O concentration, so as expected, very low hydroxide. If you're very, very high at acid, you're very low at base. Oh, they're being so nice to us. HBr is another top 6 acid, which means, again, we can say the moles of, or the concentration of acid equals the concentration of H3O, but they didn't give us a concentration this time, so a little extra work. Concentration of an acid is number of moles divided by volume, and N, curse their corrupted souls, they didn't give us the number of moles either. So number of moles equals mass divided by molar mass. The mass of HBr is 100 grams. I want to say bromine's 7990, but I don't trust myself on that one because it doesn't come up a lot. It is 7990. Okay, and hydrogen is 101, so we're going to get 8091 for our molar mass. 80.91. I'm assuming you're pretty comfortable with molar masses and this formula by now, so I'm kind of racing through it. If you are not comfortable with it, please reach out to your instructor. We are lovely people and giant chemistry nerds. Okay, so 1.236 is probably enough. We have 1.236 moles of HBr, which means our concentration is 1.236 moles divided by 0.500 liters. Concentrations are supposed to be in moles per liter, so this milliliters thing is no good. Divide this by 1,000 to get liters. Dividing by 0.5 is like multiplying by 2, so we're going to get 2.472 moles per liter of HBr. Now we can start the actual problem. They want the H3O concentration. Well, this is a top 6 acid, so the H3O will be the same number as this. H3O equals 2.472 moles per liter. The OH concentration per our formula is Kw divided by H3O. So 1 times 10 to the minus 14 divided by 2.472 gives me 4.05. Am I okay on sig digs? Yeah, 3 sig digs for this. 4.05 is correct. Times 10 to the minus 15. Again, super high acid, super low base. This is expected. Okay, E, hurting for space. I'm going to go down here for E. Sorry for the cramped real estate. My fault, I laid out this page. A solution made by dissolving 3 moles of perchloric acid. Again, top 6 acids, so at least that part isn't too bad. Our concentration for this acid will be number of moles divided by volume. So it's 3 moles in 500 ml is 0.5 liters. So that's 6 moles per liter of perchloric acid. Top 6 acids convert exactly into H3O, like 1 to 1. So 6 mole per liter acid turns into 6 mole per liter H3O. And our hydroxide concentration is 1 times 10 to the minus 14 divided by, in this case, 6. That's going to give us 1.666666666 times 10 to the minus 15 moles per liter for the OH. All these are acids, so all of these were going to have a pretty high H3O and a rock bottom OH. That was a little uncreative of the me who wrote these questions. Sorry about that. All right, 100 milliliters of dilution. Okay, they take some strong HBr and they dilute it. So we have to do a bit of a side trip here. How many moles of HBr did we have in this situation? N equals CV equals, our concentration is 0.5. Our volume is 100 mil, which is 0.1 liters. So we had 0.05 moles of HBr. They took this amount of chemical and they put it in 500 milliliters of liquid. So the actual concentration, the diluted concentration, is N over V, 0.05 moles HBr divided by 0.5 liters gives 0.1 moles per liter. Okay, and I'll say HBr again here. Hydrobromic acid is a top 6. That means it converts 100% to H3O. So the amount of top 6 acid and the amount of H3O are identical, and the formula works the way it normally does. The hydroxide concentration is 1 times 10 to the minus 14 divided by, in this case, 0.1. That'll give us 1 times 10 to the minus 13 moles per liter of OH. And finally, 25 milliliters of 0.4 mole per liter HNO3, and then adding 300 ml of water. Okay, dilution again. We need a real concentration for this, and this isn't it because this is pre-dilution. So first we're going to be doing C equals N over V to get our concentration. What's our number of moles? Well, we started with 25 milliliters of 0.4 mole per liter nitric acid. So N equals CV equals 0.4. That was the original concentration. 25 milliliters is 0.025 liters. And that gives me 0.01 moles of nitric acid. So When we dilute that, the concentration is going to be our number of moles, just found it, 0.01, divided by, careful, what's the volume? It's not 25. It's not 300 either. They said they added 300 mil. If they say that they diluted to 500 mil, that means they made this the new volume. Here, we had 25 milliliters of acid. We added another 300. Our new volume is 325 milliliters. Don't forget to turn that into liters. Sorry for all the little twists in this one, but this really is how chemists talk sometimes. So getting you used to this phrasing is a good thing. Okay, so 0.01 divided by 0.325 gives me 0.0308 moles per liter of nitric acid. Nitric acid is a top 6, so it converts 100% to H3O. So our hydronium concentration should be also 0.0308. Top 6 acids are easy. And for the last time, our hydroxide concentration is 1 times 10 to the minus 14 divided by 0.0308. And I get 3.25 times 10 to the minus 13. I hope I carried enough digits to make that work. Okay, so I'm sorry this was a little repetitive in that they were all acids. Of course, we could do the same thing with a base, find our OH concentration, and then do Kw divided by base to get the acid concentration. That would work fine. And while the question writer here was merciful and made all of these strong acids, we could just as well do this with a weak acid. We'd have to do that annoying square root Ka times acid concentration thing, but we could do that, get H3O, and then use this flip to get hydroxide. And we could even do it with strong bases if we really have to.